Okay, so welcome back, everybody. So last time I kind of ended with a list of some of the achievements of Pythagoreans. So just quickly bringing that list back. Um, so obviously the Pythagorean Theorem is one big achievement. So they were the first to prove it, as well as its converse. So last time I showed you the proof that's given in Euclid's Elements. Um, which of course was, about 200 years later. But this proof is believed to be the original proof given by the Pythagoreans. So this proof of the theorem of Pythagoras that I showed last time was something that they achieved. They investigated perfect numbers, which we're about to talk about in a second, as well as regular polyhedra, also known as Platonic solids. We'll discuss those as well today. And they discovered the irrationality of square root of 2, which caused them much consternation. This was the thing that I alluded to last time that supposedly led to them tossing one of their own overboard when this discovery was announced. So these are the three things I really wanted to focus on. So also, they investigated means that I mentioned last time, as well as what are called figurative numbers, but I'm mostly going to focus on these. So if you want to look up, so there's a little blurb at the end of, I believe this is chapter, let me see, there's a little blurb on, so this is chapter 7 in the textbook. This is mentioned, so it's like just a couple paragraphs long. Basically, it is their it's the Pythagoreans noticing certain algebraic relationships between sums of powers of numbers. Anyway, so I wanted to focus on these though. So first of all, I'm going to talk about perfect numbers. So what is a perfect number? So the Pythagoreans were very, very interested in perfect numbers. And as we'll see, we'd previously gotten the feeling that the Pythagoreans were a sort of cult. They ascribe numerical significance to everything. So they were very, very interested in perfect numbers. And as we'll see, this isn't a thing religiously or mystically. This wasn't a thing that just the Pythagoreans were interested in, but actually mystics from various types, any kind of mystic thought from various types of religions were actually interested in perfect numbers. There's a lot of different examples of this throughout the ages, and I'll mention some of those in a little bit. So what is a perfect number? So quick definition. A positive integer is perfect if the sum of its proper divisors is equal to the number itself. Okay, and so this can be a little bit confusing until I've reminded you what proper divisor means. Proper divisor means the whole list of divisors that doesn't include the number itself, right? So we know that any number divides itself evenly. It's just itself times 1. So the sum of the proper divisors is the sum of all the numbers up to the number itself. And we'll see that there's a much easier way of characterizing this in terms of a function that sums all the divisors of a number, proper or otherwise. Okay, and so examples, right? So the easy examples are 6, right? So what are the divisors of 6? The divisors of 6 are 1, 2, 3, and 6. But 1, 2, and 3 are the proper divisors, and 6 is equal to 1 plus 2 plus 3. Right? So 6 is perfect. Okay, so 6 is perfect. Another easy example is 28. So what are the divisors of 28? Well, 1, 2, 4, right, 7, right? And 14 and 28 itself. But of course, these that I've boxed are the proper divisors of 28, and we can just check that 28 is equal to 1 plus 2 plus 4 plus 7 plus 14. Well, let's just check here. So 7 plus 14 is 21, plus 7 is 28. Yep, that's right. So this is another example of a perfect number. Okay, and these two were well known to the Pythagoreans. And what I'm about to show you is that it's believed that a lot more was known. A lot more of this was known to the Pythagoreans. In fact, a very general way of generating some of these is also known to the Pythagoreans, it's believed. So, what is a maybe more mathematically convenient way of characterizing this? Well, what do you notice about these sums if let's say that I didn't pay attention to this word proper divisor here in this definition, and instead I accidentally, when I was doing these sums, I accidentally included here, maybe I'll do it in another color. So let's say I accidentally included all the divisors. So rather than summing just the proper divisors, that is all the divisors that doesn't include the number itself, I also accidentally summed the number itself. How does that change what I get here? Well, here I would have 1 plus 2 plus 3 plus 6. But we know that 6 is a perfect number, so everything that came before is already 6, so it's 6 plus 6, right? It's 12, or 2 times 6. Okay. Similarly, if here I accidentally summed 28 here as well, well, I already know that everything that comes before it sums to 28 because it's a perfect number. So 28 plus 28 then would be 2 times 28, right? Or 56. Okay. And so rather than having to rely on this subtle word of putting proper divisors here, I could just say a perfect number is a positive integer such that when I sum all of its divisors, I get 2 times the number itself, right? Okay. All right, and so that's exactly what I'm going to do, because that way of characterizing it is a lot, it's a lot more convenient mathematically to write it that way. So that's what I'm going to do next. So if n is a positive integer, okay, let sigma of n be the sum of all of its divisors. Okay. Then our new definition of perfect number. So n is perfect if sigma of n is equal to 2n. Okay. So this is a more convenient way of dealing with this. So a number is a perfect number if when you sum all of its divisors, you get 2 times the number itself. Okay. Now, here's the fact. So here's a theorem. Now, this theorem is from this is from book. So when I say book of the elements, the books of the elements are what we would call chapters today. So so book 9 of Euclid's Elements. This is this is Proposition 36, I think. Proposition 36. So this was known to the Pythagoreans, or discovered by. So known by Pythagoreans and likely discovered by the Pythagoreans. Okay, but recorded in Book 9 of Euclid's Elements. As I've mentioned before, Euclid's Elements are from approximately 300 BC. So if you're keeping track, we're talking about the Pythagoreans, which of course first flourished in the 500s. Okay. So this came much later, but this was almost certainly due to the Pythagoreans, but it's proved in Euclid's Elements, and I believe this is the first known proof of this fact. So here is the following fact: if n is a positive integer of the form n is equal to 2 to the m minus 1 times 2 to the m minus 1, okay, where 2 to the m minus 1 is prime, then n is perfect. Okay. All right. And so if we have a positive integer that looks like this, it's 2 to the m minus 1 times 2 to the m minus 1. Okay. Where this 2 to the m minus 1 is prime, then this is a perfect number. Okay. So here's the proof of this fact. Maybe I'll scoop this up so that you can actually see what's going on here. So the proof is done the following way. So if we call this 2 to the m minus 1 a prime, right, if that's prime, we call that p. Okay, then the divisors of n, so n, of course, is 2 to the m minus 1 times 2m minus 1, or we'll say p. Then the divisors of n are the following. What can the divisors possibly be? If this part, right, of n is prime, so 2 to the m minus 1, this is prime. Other than that, we just have powers of 2 here. So we have some power of 2 times a prime number. What are the possible divisors of this? This is why it's so important that this thing be prime, because if this weren't prime, we wouldn't be able to easily list out all these divisors. But because this is prime, what are the possible divisors? Well, any power of 2 up to 2m minus 1 divides n, right? So 1, that's always a divisor. 2 is going to be a divisor as long as m is 2 or bigger, right? So 1, 2, 2 squared, 2 cubed, all these powers of 2 are going to divide this all the way up to 2 to the m minus 1. Right, so there's a list of things that divide this. Okay, what else? Well, p, the prime itself, divides this, of course. Right, and what else? Well, powers of 2 times p. So 2p, 2 squared times p, and so on. Right, all the way up to n itself, 2 to the m minus 1 times p. Okay, so quickly, why can we say that this is the exhaustive list of divisors? Well, once we have n factored like this, these are the only things that we can have, because p is prime. So this doesn't split up further into factors, and so if that were the case, we wouldn't be able to list this very nicely at all. But because p is prime, we know that it itself has no divisors other than 1 and p. So then looking at this is just some power of 2 times a prime number, and this is the full list of divisors. And of course, there's something to be said here, that here, since p is prime, 2 to the m minus 1 times p is the prime factorization of n, and this is unique, as we said before, because there's unique factorization. So I have the unique prime factorization of n. There it is. This allows me to easily list out those divisors. Okay, so that's all of them. Okay, so what this means is that I can just compute this sigma of n, right, by summing all of these things. So that's exactly what I do. I sum every single one of these things. So I do 1 plus 2 squared plus 2 cubed all the way up to 2 to the m minus 1. And then I add to that the remaining ones, right? So I add that the remaining ones. I'm going to put them down below so it makes it easier to see. Plus p plus 2p plus 2 squared p, and so on all the way up to 2 to the m minus 1 times p. Okay, so here's my big sum. All right. But I can simplify this a little bit. So I have 1 plus 2 squared plus 2 cubed, and so on, all the way up to 2 to the m minus 1. And then on the second line, I have the same thing, but there's a factor of p in each term. So what this means is that I can factor this, right? I can factor this by pulling out this sum. So I have this sum times 1, and I have this sum times p. So really what I have is this sum times 1 plus p. Okay, so I'm just factoring here. All right. But there's a more convenient way of writing this sum. Okay, what is that? So let's do a little aside here. Let's do a little aside. Let me get a clean sheet of paper. So I have this quantity, 1 plus 2 squared, and so on, all the way up to 2 to the m minus 1. And I claim there's a much more convenient way of writing that. Okay, and the more convenient way of writing that is this is the same as 2 to the m minus 1. How can that be? Well, let's try a couple of examples to show that this actually works out. So let's do 1 plus 2 squared plus 2 cubed. Okay, what is that? So let's just do that. This is 1 plus 2 plus 4 plus 8. So 1 plus 2 plus 4, that's 7, plus 8 is 15. So is that equal to 2 to the 4th minus 1? Well, 2 to the 4th is 16, minus 1 is 15, yeah. That's right. Let's do one more to convince ourselves, right? So 1 plus 2 squared plus 2 cubed plus 2 to the 4th. What is that? Well, that's 1 plus 2 squared plus 2 cubed. I already saw that was 15. So that's 15 plus 2 to the 4th is 16. So this is 31. And is that equal to 2 to the 5th minus 1? Well, 2 to the 5th is 32. Minus 1 is 31. Yeah. What's going on here, right? There's a number of ways you can see what's going on. So on one hand, let's start with this example, right? So with this example, I'm going to rewrite this. So 1 plus 2 squared plus 2 cubed plus 2 to the 4th. Of course, if we viewed this as a proof, then we'd kind of sort of be thinking like the Babylonians or the Egyptians here, right? Where no proof not needed. I see a couple of examples and I'm good to go. Of course, there's a lot of pitfalls with that. And I'll show some examples later of where you say a statement and it's true for like the first, 100 values, and then it's false, and then forever false after a certain point. So let's say we have this. Okay. Now, what I want to do is a little algebraic trick. What I could always do here is add 1 and subtract 1. Oh, that doesn't make much sense if I do it on this side. So let's add 1 and subtract 1, right? I can do that always, right? But what happens when I add 1 and subtract 1? So adding 1 and subtracting 1, I can move this 1 over here. This 1 goes here. So I have 2 plus 2 squared plus 2 cubed plus 2 to the 4th minus 1. Well, now this 2 plus 2 is 4, which is actually 2 squared. But then I would have 2 squared plus 2 cubed plus 2 to the 4th minus 1. But then this 2 squared plus 2 squared is actually 8, which is 2 cubed. So this is 2 cubed plus 2 cubed plus 2 to the 4th minus 1. But then 2 cubed plus 2 cubed is 2 times 2 cubed, right? It's 8 plus 8. So it's 16, which is 2 to the 4th, plus 2 to the 4th minus 1. And so now, lastly, you see 2 to the 4th plus 2 to the 4th is the same thing as 2 to the 5th minus 1. Oh, I'm a little bit off screen. There we go. So that's a neat algebraic thing that happens, right? Okay, and so you see exactly this inductive step now. Of course, you can prove this with induction. There's any number of ways you can prove this. You could just actually do the algebra if you like, but you could also do this with induction, right? So you could start with base case m is equal to 1. It's true, because in that case you would just have 2 to the 1 minus 1 is 1, which is 2 to the 0. So that's fine. And then, the inductive step, you can do it in one go. You're trying to show that 2 to the m plus 1 minus 1 is equal to this sum up to 2 to the m, and it is. So maybe I'll leave that to you all. So by induction, you can rewrite this. This is the main thing we're trying to do. Okay. So we're rewriting that bit, that sum, as 2 to the m minus 1. Oh, a little bit off the page. There. All right, so I'm rewriting that sum as 2 to the m minus 1. So this becomes 2 to the m minus 1 times 1 plus p. Okay. So how does this help us? Well, p was of a very particular form. P was 2 to the m minus 1. So what is 1 plus p? Well, 1 plus p is 1 plus 2 to the m minus 1. So it's actually just 2 to the m. Okay. So then this is equal to 2 to the m minus 1 times 2 to the m. I'm going to swap these around. I can do that. So this is 2 to the m times 2 to the m minus 1. We're almost done here. I can factor out a factor of 2 here and turn this to 2 times 2 to the m minus 1 times 2 to the m minus 1. Okay, why did I do that? What is this? This is n. So this is 2n. So sigma of n, that is the sum of all the divisors of a number that looks like this, is equal to 2n. That's it, because that is my definition of a perfect number. All right, so thus n is perfect. And this is the exact proof given by Euclid. Okay, so thus n is perfect. Okay. Now, the reason why that is important is because this one gives a way of generating perfect numbers. And as we'll see, it actually is the only way to do it if the perfect number in question is even. So I'll mention more about that in a few minutes. But thus, generating perfect numbers is related to figuring out when 2 to the m minus 1 is prime. Right? That was what was required. Okay, so if you go back to that theorem we just proved, what was required is that 2 to the m minus 1 is prime. So whenever 2 to the m minus 1 is prime, this number n formed in this way is guaranteed to be perfect. That's what we proved. And so if you know exactly when 2 to the m minus 1 is prime, you can generate perfect numbers like this. Now, the question is, can you generate all of them in this way? Unknown. Currently, still unknown whether or not you can generate all the perfect numbers like this. Okay, I'll go through the list of what we know about perfect numbers in a little bit, but currently unknown whether or not we can actually generate all of them in this way. But the point is that this is a way of generating them so long as 2 to the n minus 1 is prime. This is a very special type of prime, it turns out. So here are some facts. So fact, 2 to the m minus 1 is prime if and only if m itself is prime. This is actually never prime. So this is never prime when m itself is not prime. Okay. Now, oh, I shouldn't write. This is not if and only if. This is only a one-way. This is a one-way implication here. Yeah. So the backwards direction is very false. So the forward direction is 2 to the m minus 1 is prime. If that's the case, then m is prime. The opposite direction is not the case, okay? So the converse is not true. So for instance, m equals 11 is prime, but 2 to the 11 minus 1 is 2047. But 2047 is 23 times 89. So not prime. Okay. But when these are prime, they have a special name. 2 to the p minus 1 is called a Mercen prime. If it is prime. Okay. So you may have heard this before if you've taken any number theory or if you have even been casually interested in prime numbers or number theory. Okay. So a lot can be said about Mercen primes. So first of all, notice this is an exponential quantity, right? It's 2 to a power minus 1. Okay, the minus 1 is basically insignificant as p is getting larger and larger here, right? And so what this means that it's an exponential quantity is that this gets huge really quickly. So even for very relatively low powers of p, this thing is huge. Okay, so Mersenne. So this is named after a guy. The guy's name is Father Mersenne, and this is he was born in 1588 and died in 1648. So he claimed that the first 8 perfect numbers are given by the values. So claimed correctly that the first 8 perfect numbers are given by m is equal to 2, 3, 5, 7, 13, 17, 19, and 31. Okay. All right. And so you can actually check the form of the perfect numbers we showed before to actually see some of these. So let's do that now. So when m is equal to 2, what was the form? So we said that this was 2 to the m minus 1 times 2 to the m minus 1. So when m is equal to 2, what number do I get? I get n is equal to 2 to the 2 minus 1 times 2 squared minus 1, So 2 to the 2 minus 1 is just 2 to the first, so that's just 2 times 4 minus 1 is 3. 6. That's the first perfect number. Yep. What about m is equal to 3? So then n is equal to 2 to the 3 minus 1 times 2 cubed minus 1. So this is 2 to the 3 minus 1, that's 2 squared, times 2 cubed minus 1 that's 8 minus 1, so that's 7. 4 times 7 is 28. All right, let's just do one more. So m is equal to 5. What is the next perfect number? Then n is equal to 2 to the 5 minus 1 times 2 to the 5th minus 1. So this is 2 to the 4, that's 16, times 31. So what's 16 times 31? Let's see, that's 10 times 31, so 310 times 100 or plus 186, so 496. Is that right? Did I multiply those correctly in my head? Maybe. Okay, so that's the next perfect number unless I screwed up that multiplication, which is definitely possible, but anyway. And of course, following these claims is the implicit assumption here that 2 squared minus 1 is prime, which it is. It's 3. And that 2 cubed minus 1 is prime, and it is because it's 7. And that 2 to the 5th minus 1 is prime, and it is because it's 31. Okay. All right. Good. Chat says I did that multiplication correctly. So 496 is the next perfect number. Okay. And so, Mersenne, so these were correct. He was correct in generating the first 8 perfect numbers. But Mersenne also checked, or also claimed, that 2 to the 67 minus 1 is prime, but he was wrong. So he was not shown wrong until, I believe, 1903. So in 1903, let's see, it was Frank Nelson Cole. Factored 2 to the 67 minus 1. Which he worked out on a... Oh, why am I so off screen? Jeez. Okay, so Frank Nelson Cole factored 2 to the 67 minus 1. And he did this in a lecture where he didn't say a single word, apparently. He just did a gigantic multiplication, and he factored it as 2 to the 67 minus 1 is equal to 193,707,721 times 761,838,257,287. So if you multiply these two numbers together, you get 2 to the 67 minus 1. So apparently he did this computation on several blackboards without saying a single word and got a standing ovation when he was done, and he actually checked, that everything worked out. So, anyway, this is pretty, this goes to show that, right, 2 to the 67 minus 1 is already a huge number. And that's with an exponent of 67, right? So there's some problems here with doing things by hand. In fact, before the computer age, I believe, I can't remember exactly how many, so yeah, before 1950, right? Before 1950, only the first 12 Mercen Primes were known. Okay. And the way that this goes, again, this is an exponential quantity, so it is, it just gets worse and worse, quicker and quicker. It's not ideal for human computation. So computers vastly improved the ability to actually find these things. There's what's called the Mercen Prime hunt or prime search that you can have a look at. That is basically a project to use tons and tons of computing power to search for the next Mersenne prime. The largest prime number known at any given time is likely to be a Mersenne prime. There are some other special forms of primes that occasionally will take the crown, but I believe for the last like 10 years, the greatest prime number known is a Mersenne prime. In fact, currently the largest, or at least as of like October 2020, so the current largest known prime is a Mersenne prime. And that current largest known prime, let me pull it up here. Yeah, so it is 2 to the 82,589,933 minus 1. Okay, so this is the largest, this is the 51st Mersenne prime. Okay, and largest known prime. For the past 24 years, every Mersenne prime that has been found using this Mersenne prime search, the Great Internet Mersenne Prime Search, GIMPS. Okay, is the program responsible for finding all of these since '97. Okay, this has, how many digits does this have? Let's see. It has about 29 million digits in base 10. So this was found in 2018, I think. Did they hold any practical significance? They held mostly religious significance, not even just for the Greeks. So as we'll see here in a second, I'll mention the other examples of other religions being interested in perfect numbers. What do we know currently about perfect numbers? Okay, because as we see, there's this relationship between Mersenne primes, which 51 of them are all that we know, right? And speaking relatively, that doesn't seem like we know that much. Can I write out that prime? That might take a while. Although I'm sure you can view a printout of it somewhere if you look up the largest currently known prime, I'm sure that there's someone has printed out at least a good portion of it. So, what do we know about perfect numbers? Because they're related to Mersenne primes, it's not currently known if there's infinitely many Mersenne primes. So one, not currently known if there are infinitely many Mersenne primes. I mean, we've only found 51, right? Okay. It is not currently known if there are any odd perfect numbers. This is frequently referenced as one of the things that seems like it should be easy, or it seems like it shouldn't be too hard. to show that there can't be any odd perfect numbers, but this is actually ridiculously hard, and it's not currently been done. So whether or not there are odd perfect numbers is not known. Okay. Okay, but every even perfect number must be of that Euclidean form. That was known to the Pythagoreans. Okay, and so this fact that was discovered by the Pythagoreans is actually, it is basically, as far as we know, it's basically the only way, it is the only way a perfect number can show up. Okay. So this was first proved by Euler. So this number 3 was first proved by Euler in the 1700s. So I'm not going to go into that proof here, but if you're interested in it, it is on page 39 of the textbook. So this was first proved by Euler in the 1700s. Okay, that every even perfect number has to be of that form. Okay. Now, the examples, since I was asked about their significance. Basically, there's many examples of people being interested in perfect numbers religiously. So, the Pythagoreans held that perfect numbers were religiously significant. Of course, for the Pythagoreans, right, most numbers were religiously significant. That is, if they were rational numbers, they were religiously significant. So maybe it's not so surprising. But they weren't alone. So here's some other examples. So, for instance, St. Augustine, writing much later in City of God, makes specific reference to this. In fact, the passage in question, so this is directly quoted from Augustine's City of God. So 6 is a perfect number in itself, and not because God created all things in 6 days. Rather, the converse is true. God created all things in 6 days because this number is perfect, and it would have been perfect even if the work of 6 days did not exist. So that's a pretty big claim, right? That actually, the perfection of the number 6 is what dictated the creation to occur in 6 days, right? So that's a pretty big claim, right? So St. Augustine, so 6 days creation directly as a result of perfection of 6. And I guess that, makes a little bit more sense than 28 days or 496 days. Maybe they don't have the same snap to them. So 6 days creation directly as a result of the perfection of 6. This is claimed by St. Augustine. Sufis stated that 6 is the first complete number and 28 is the second. So Sufi mystics, there's no source here for exactly where this comes from, but apparently 6 and 28 listed as complete numbers. Okay. There's an Arabic mathematician, Ibn Qura. So this was much later. This was 826 to 901 is when he lived. Gave a general method for constructing several amicable pairs. Now you might say, well, amicable pairs are not really the same thing as perfect numbers. They're not, but they're related because it's specifying that the divisors or the proper divisors of some number add up to a specified amount, right? So, for instance, the Pythagoreans supposedly only knew one amicable pair of numbers, which is the pair I mentioned before, 220 and 284. Yeah, so the Pythagoreans apparently only knew that 220 and 284 were amicable and didn't know any others. And Euler found 60 other pairs of amicable numbers, but actually I think he missed the second smallest pair of amicable numbers, which is 1184 and 1210, which were only discovered in the 1800s. That's to say that perfect numbers and amicable numbers and questions, these very seemingly simple questions coming from basic number theory can be a lot more involved than you might think. Okay, and so the next topic that the Pythagoreans touched on they were very interested in was the topic of regular polyhedra. And so before I mention the regular polyhedra, what I will say is this is going to be, describing these is going to be related to the description of a plane being tiled, right? So imagine I want to create a tiling of the plane, but I'm not allowing just any shapes to do this. I want to do this via regular polygons, right? So what are my options here? So I can do this with triangles. I can do this with squares. I can do this with hexagons. Can I do it with any other regular shapes? Well, the answer is no. But why is the answer no? Because if I'm trying to come up with a tiling, right, the one by squares should be obvious. If I'm considering this paper the plane, then the one by squares is, oh, I did a really bad job there. The one by squares is the tiling that looks like this, right? And of course, pretend that I did a much better job and that these squares are all the same length. The idea is that at a vertex of this tiling, so the vertices will be these points of intersection, right? So at any vertex, right, what has to be true? Well, first of all, let's look at what is true for this tiling. So what's true about the angles around this vertex? Since these are regular polygons, what does regular polygon mean? Regular polygon means all of its side lengths are equal and all of its angles are equal. Okay, so that's what a regular polygon is. And so because of that, because it's a regular polygon, all these angles that meet at a vertex have to be equal, right? So if all these angles have to be equal, then the second you know how many polygons are meeting at a vertex, then you know what the angles have to be, right? And so in the case of squares, how many polygons are going to meet at a vertex? Well, 4. And since those 4 angles have to be equal to each other, it's just the total possibility, right, which is, if we're doing the Babylonian thing here and we're saying that this is 360 degrees, right, then in 360 degrees, divided evenly 4 ways, each of these angles has to be 90 degrees. Of course, you knew that those angles were 90 degrees because these are squares, right? The point being that if I try to form a tiling of the plane, and the sum at each of these vertices that I get is less than 360 or more than 360, this tiling's not going to work, right? So you're restricted in a way by what the size of these angles in a regular polygon are going to be, right? So for instance, we can work out what the angle measurements an irregular polygon have to be. And once we know that, this nails down exactly what our options are for tiling the plane. So I've run out of time, but we'll do this at the beginning of class next time. So we'll go over regular polyhedra, and we'll go ahead and we'll actually mostly finish that and talk about the crisis of incommensurables. So what the Pythagoreans uncovered when they uncovered the square root of 2 is irrational, and how this influenced the rest of Greek math. Okay, so anyway, so that's that. I will see you all on Monday. As I said, I still haven't posted homework, so don't think you've been missing anything. I will post it soon. I keep saying that, but I will actually do it. So anyway, I will see you all on Monday.